Welcome back to the third video in the electronics series, and in this video we're going to look at cascading amplifiers. Now sometimes one amplifier isn't good enough, so we have to cascade them. And also, maybe sometimes one view is not good enough for the YouTube algorithm, so if you learn something in these videos, like, comment, subscribe, helps me crawl out of the bottom of the YouTube algorithm. But anyways, if we have cascaded amplifiers, essentially we have one amplifier here on the left, where we have an input denoted by the subscript 1. We have an output that is tied to the input of another amplifier, and then we have our final output. And we know that the output voltage of that first amplifier will be the voltage gain times the input, and it will follow through for the second amplifier. But what we notice is that the input for the second amplifier is equal to the output of the first amplifier. So what we can say is that the output voltage VO2 of the entire system is equal to the voltage gain of the second amplifier multiplied by the voltage gain of the first amplifier times the input of that first amplifier. And from this entire system, we can say that the overall voltage gain is equal to the output of the second stage divided by the input of the first stage, which is equal to the product of both of the independent or individual amplifier voltage gains. Now we could take the example above and expand it in our voltage amplifiers that we've been working with. So right here on the left, we have our first stage, then that's connected to our second stage, and then after the second stage, we have some load. Now just focusing on the output of the first stage, right here, we can see that we have a dependent voltage source, where we have that open circuit voltage gain right here, times the input, and we're able to find what the output VO1 is going to be equal to. Just the open circuit voltage gain times the input, and then we have the familiar resistor ratio right here. We can divide the output by the input simply to get our voltage gain of that first stage, which is equal to this term here. And we can do the same for the second stage. Now through substitution, we know that the input VI2 is going to be equal of the output VO1, so we can substitute that in right here. And we can also divide the output of the second stage by the input of the second stage, simply to find the overall voltage gain of that second stage. That's going to be equal to AV2. Now we can divide the output voltage VO2 by our input from the first stage, VI1, using this equation. And that's going to give us our voltage gains for each amplifier. Now for the entire system, we could simply define that entire voltage gain by A subscript V. So that's how we deal with cascaded amplifiers. It can get a little bit tricky if you have several of them, keeping track of the voltage gain or the open circuit voltage gain for each amplifier, something to take note of. But a little trick that might be useful is that if you have a bunch of amplifiers, you can undo the cascading effect and group them all into one amplifier. Which also says if you have an amplifier specification that you need to meet, you can do the reverse again and combine multiple amplifiers to get that overall spec that you're trying to meet. So if we consider the example above, we can actually collapse it into this amplifier right here, where we simply have this A subscript V term here, and just VI, where VI is our input, and that's going to be equal to our input above, VI1, and our output VO is going to be equal to our output from VO2, or that second amplifier from above. So if we scroll back up, essentially what we've done is collapse all of this. So we kind of just have this left side and this right side, but all of this is kind of baked into that new dependent voltage source right here. So we're going to return to an old topic that we talked about in the advanced circuit analysis course, and that's going to be the decibel scale. So what we can do is consider the gain in the decibel scale simply by GdB, and that's going to be equal to 10 times log base 10. But we can recall from previous videos that the power gain is equal to the output power divided by the input power, which is also equal to the voltage gain squared, and then we have this ratio of the input resistance or impedance divided by the load resistance. Now if GdB is less than 0, the output is smaller than the input, which isn't really what you want to have for an amplifier, but this is actually an attenuator. But we're not going to talk about that too much in this course because it's introductory. We'll get to it in a later course. Now for a cascaded system, we can look at GdB, which is again 10 times log base 10, and then the product of G1 and G2, which by our rule of logs, shout out to Paul Bunyan, we can break that up into 10 log base 10 with G1, and then 10 log base 10, then G2. And this is going to be equal to 20 log base 10 of our voltage gain, plus 10 log base 10 of our input resistance, and then minus 10 log base 10, and we have that load resistor right there. So what we can see here is that in the dB gain, we do have the voltage peaking in there, or the voltage gain. And we know that the voltage gain is not going to be equal to the power gain. Just keep that in mind. In the dB scale, our voltage gain, AV dB, is equal to 20 log 10, and then AV, or our voltage gain, and the current gain, AI dB, that's going to be equal to 20 log 10, and then we have AI. And if you recall from the advanced circuit analysis course, when we started to look into the dB scale or decibel scale, we were kind of starting to look into frequency responses. So these input resistances or load resistors could be different components like capacitors and inductors. So we have some kind of frequency response there that could roll off or increase, and we could have all these different kind of frequency responses. In the next video, we're going to look at some more amplifiers that may be useful towards your education. Thank you for watching, and we'll see you there.